this lecture, we will discuss together pipe network analysis. In last lecture, we discussed branching network design. In the case for design, we look for the diameter of the pipe and we look for the head at the connection points. But for the pipe network analysis, everything about the pipes is given. The only thing we would like to look for the flow rate. We would like to estimate the flow rate in each pipe and also to evaluate the head at the nodal points. So the network already exists with diameter and length and everything, and we would like to estimate the flow rate. The head loss relation is given as H losses equal certain resistance R multiplied by Q raised to the power N. I would like to stress here, R has certain dimension. Possible values of N, for example, N equal 1 for laminar flow, since H losses equal F L over D V square over twice G, and F has V in the denominator, so H losses will be related to velocity to the power 1, i.e. the flow rate also to the power 1. That's for laminar flow. For fully turbulent flow or complete rough, N equal 2. For smooth pipe, N equal 1.75. I mean smooth pipe and also turbulent flow. For if we use Hazen-Williams relation that we discussed last lecture, N equal 1.85, as you can see. Now, the resistance, as I said, has certain dimensions depending on N, e.g. for N equal 2, R has a dimension of T square L minus 5. In SI units, it's second square divided by meter to the power 5. We have to apply for the network 2 rules. The first rule is to satisfy the mass conservation for each nodal point and for the whole network as one unit. For each nodal point, the mass flow coming in equal mass flow leaving out. For the whole network, also the mass of the supply, mass flow rate of the supply equal the total sum of the demand. That's the first condition. It looks like very similar to Kirchhoff law for the electricity. The current into the nodal point equal the current out of the nodal point. The second rule is the sum of friction head loss should be 0. You take one direction to be positive and the other direction to be negative, and the sum with sign should be 0 because you come back to the same point. So the sum of the head loss with sign will sum to 0. If the condition 2 is not satisfied, we make correction delta Q for each loop. Now, if we make the correction, then sigma R for each loop multiplied by Q plus delta Q to the power N equals 0. And you can expand this summation into summation of R Q to the power N with sign, and then summation of N R Q to the power N minus 1 delta Q. And if you look at the next term will be N multiplied by N minus 1 divided by factorial 2 R Q square Qn minus 2 delta Q square and so on. But we only take 2 terms for this expansion. And from these 2 terms, we can get delta Q equal minus sigma R Q to the N with sign divided by sigma absolute NRQ to the power N minus 1. Okay. Again, take one direction, for example, clockwise to be positive, and the other direction should be negative in In the denominator, take only absolute values, as I said. This I can prove to you if you come to my office for some discussion. As an example of if we would use Darcy-Weisbach relation with HL equal FL over D sigma K for minor losses multiplied by V squared over 2G and consider V to be Q divided by the area, okay, you can get R like this and N equal to. Anyway, from information about the length, friction coefficient, diameter, sigma Q, the diameter again here, you can get what is the value of R in your relation H losses equal R multiplied by Q to the power N. We will consider a network made of 4 pipes with one supply node at A with a given head at HA equal 10 meter. Pipe AB has a resistance 50 seconds squared divided by meter to the power 5. BC has 30. R for CD equal 20. R for AB equal 40. Demand at B, C, and D are given 0.2 meter cube per second, 0.2 meter cube per second, and 0.1 meter cube per second, respectively. We need to find the discharge at each pipe and the head at each nodal point. Okay, now I have this loop. It has 4 pipes. Each pipe has the resistance above it, R equal 50 for AB, R equal 30 for BC, R equal 20 for CD, R equal 40 for DA. Now we assume the discharge. As you can see, at point A, we have 0.5 supply. We divide 0.3 and 0.2. You can make any assumption. It will converge. If your assumption is logic, so the number of iterations will be less. If the assumption is far from logic, you may take some more iterations, okay? But the method is converging. The method is actually referred to Hardy-Cross method. Hardy-Cross method is how to calculate the flow rate in a pipe network. It's very, very simple method. It can be used in a calculator. It can be also programmed by any language. Very simple method of calculating the flow rate in each pipe. Okay. Now we have this table. Pipe, the first column, the resistance, the second column, the discharge in the third column, then RQ square in the fourth column, and 2RQ in the fifth column. Okay. For AB, we get again here, we take clockwise to be positive and counterclockwise to be negative. So with this assumption, you can see in AB, the friction here is positive. BC also is positive. CD will be negative, and the DA will also be negative. Okay. I would like again to make sure that the mass conservation satisfied. It is satisfied for the whole loop. The supply is 0.5, and the total of the demand is also 0.5. 0.2 plus 0.2 plus 1 is 0.5. So the mass conservation is satisfied for the whole loop together. The mass conservation also satisfied for each nodal point. Here coming 0.5, 0.3 goes in AB, and 0.2 will go to AD. At B, we have 0.3 coming into B and leaving 0.2 in the demand and 0.1 in the pipe BC. At the point C, we have 0.1 coming in from BC, 0.1 coming from DC, and 0.2 is a demand at point C. Again, 0.2 here is meter cube per second. Okay, the resistance R is second square divided by meter to the power 5 to satisfy the relation H losses equal R multiplied by Q square. Okay, now we calculate, note that for pipe AB and BC, the pressure drop here is positive, is positive. For the 2RQ, we don't take any sign. We take the absolute always. So this column, the fifth column, we have absolute values, no sign. But for the fourth column, depend upon the direction. Clockwise positive, counterclockwise is negative. And then you get the summation, and the summation of RQ square with sign, the plus 3, because we have 4.5 plus 3, 4.8, minus 1.8, you get 3. Now twice RQ is 30 plus 6, 36, plus 4, 40, plus 15, 16 is 56. We divide, get delta Q equal the summation of RQ square with a negative sign here, divide by the summation of twice RQ, we get the correction. The correction became to be negative. Correction negative, so it will be added for the negative flow pipe, and it will be subtracted from the positive flow. And then again, if we start with assumption satisfying the mass conservation, also after correction, it will satisfy also mass conservation. Because for each loop, we have delta Q. We may have many loops, but I'm trying to give you a very simple example to capture the idea. Okay? Now, we make the correction. We put the flow rate after correction. For the correction is negative, so for the pipe AB, it's subtracted. For the pipe BC is also subtracted. For pipe CD, it is added. For pipe DA, it's also added because the correction is negative and the initial value is negative, it's added. Okay. Now, I would like to show you this. The first correction was 0.05, but the second correction 0.001, which is much smaller. That means we are going in the right direction for the conversions. The convergence process is working, or the method is converging. Hardy-Cross method is a converging procedure for finding the flow rate in a pipe. Now, we come to the point we would like to calculate the head. We usually, the demand point, the head is unknown, but the supply point have certain head. So HA is a supply point here. We have HA equal 10 meters. Okay, if we have more than one supply point, then we have to make the so-called pseudo loop. I think it's beyond the scope of this course, so we'll not come to this for our problems. So we have only one supply point with given head 10 meters. Okay, now, since the flow is coming from A to D, for example, from A to D, so HD will be equal HA minus R in the pipe AD multiplied by Q square in the pipe AD, where, and this, since the flow is coming from A to D, that means D has less head. With the word head here, as I mentioned the last lecture, I mean piezometric head. Piezometric head is a summation of P over rho G plus Z. P over rho G, it's kind of adding the potential energy to the flow energy or to the pressure energy. So when we talk about H here, it's actually H star, which I usually call it piezometric head. If you have a manometer, you measure pressure or measure head, it will be piezometric head. Anyway, then we get 7.4 for the head at D. Also at B, since the flow is coming from A to B, so the head at B, the piezometric head at B, should be less than the piezometric head at A by RQ squared. R for the pipe AB and the Q in the pipe AB as well. So HB equal HA minus R AB multiplied by Q squared in the pipe AB. And then you get HB as it's given here, around 7 meters. Okay, how about HC? HC should be less than HB. Why? Because the flow is coming from B to C. The flow is always from high energy level point to a lower energy level point. Okay, so HC equal HB minus R from B to C multiplied by Q squared from B to C. And then you get the head at C. Okay, it came to be 6.928. Okay, now how about HD? HD, note that the flow is coming from D to C. So the head at D or the pressure at D should be higher than the pressure at C. Since we have the head at C, so we say HD equal HC plus RCD multiplied by Q squared, and you get the head at D equals 7.406. And then initially we have balanced continuity equation for each node, and we end up also with balanced continuity equation for each node. Okay, if you have any question, please don't hesitate to call me or maybe to send me a message or something. I will ask Dr. Mina to put this lecture in your meeting that you usually have before, so we benefit from his experience on this. But don't hesitate to call on me for any specific question for the pipe flow. We discussed together also the dimension analysis. If you have any question on this, you can call me anytime. Thank you and good luck, and stay healthy, please.